Hi, thank you so much for having me at this delightful event. I want to tell you some combinatorial aspects of a topic that I've spent quite a lot of time on recently, and in fact, up to 10 years ago during my PhD thesis, even further back. Um, let me give you some references, and then the rest of this will be sort of board talk, so to speak. I have two recent-ish papers joint with Brown, Galatius, and Payne, and very recently joint with Asaf, Brandt, Bruce, and Vlad. And they touch, they're both long papers, but what I want to present today, which is about moduli of tropical abelian varieties, is somehow a thread in both of these papers. And if you want a friendly introduction, if you don't mind, I'll suggest an old paper of mine, which has definitions, combinatorics, and pictures. That's the reference at the bottom. So let me tell you what I want to tell you. I promised a talk that is certainly doesn't require any prerequisites in tropical geometry. So I would like to start by telling you approximately what I mean when I say that I study tropical geometry. This is the study. It's a field, so this is not an official mathematical definition, but let me say that it's the study of combinatorial structures arising in the limit, or perhaps, if you will, at infinity, in the study of varieties. Algebraic varieties, spaces that are locally modeled by polynomial equations. And you may have varying levels of previous engagement with this field. Sometimes people give talks about tropical geometry and you see sort of polyhedral pictures in R2 or R3 that might look something like this. This would be the sort of tropical analog of studying a plane curve construed like that, the sort of classical study of plane algebraic curves. But what I'm studying, what my focus is in tropical geometry, it's a bit different, although it falls under the same heading of studying combinatorial structures in the limit. Here, what I'm studying is a situation where you might have, let's say, a degenerating family of algebraic varieties. For example, this family of Riemann surfaces that is becoming closer and closer to singular. When I say a family of algebraic varieties, I mean formally one big variety, but perhaps fibered over a base. Like, for example, think of this as a family of degenerating algebraic curves of genus 2. And in the limit, one wants to associate a possibly singular object in algebraic geometry, but in tropical geometry, we take that to the extreme. We might associate a combinatorial object. So if this is a family X, perhaps, we might associate to X a tropicalization which records some combinatorics of the limiting object, here, the singular Riemann surface. So this is an example taken from sort of tropicalization of algebraic curves, where one associates a graph to an algebraic curve. The graph has combinatorics that holds the data of the number of components of the curve, the way in which they intersect, and in this case, the genera, the topology of each individual component. Here today we will study tropicalizations of suitably nice, also called normal, so formally normal crossings, or toroidal. Compactifications. And let me give you a small example before launching into the main example I wanted to share with you. So today's, let's start with a cartoon example. So consider toric geometry, toric varieties. And one small example to start with is a two-dimensional torus which can be compactified by the projective plane, the complex projective plane, sorry. This is an example of a toric variety. It has a boundary. In other words, we add something to go from the two-dimensional torus to projective space. The torus can be viewed as inside projective space, those points x, y, z, such that x, y, and z are all non-zero. And so what's interesting as a tropical geometer is to consider what we added. I claim that we added 3 so-called divisors. So the part where x could be 0, the part where the coordinate y is 0, and the part where the coordinate z is 0 is what was added to c star squared to get P2. Combinatorially, one associates the dual complex, the so-called dual complex, which is in this case, simplicial complex that merely records the combinatorics of the pieces you added and the way in which they intersect. So here I have the one skeleton of a two simplex, so a triangle, not filled in. It has 3 vertices corresponding to the 3 pieces I added, and every pair meets at an edge because every pair of divisors here meets at one point. And for us, it will be convenient to do the following, which is not too important, but can make some of my bookkeeping easier. For geometric purposes, I'll consider not just this triangle, but a sort of infinite cone over that triangle. So this is the tropicalization. Sorry about this picture, but this is supposed to be an infinite cone. So it's like a 3-sided infinite ice cream cone. And this, for me, is the tropicalization of this pair. So in some sense, it is about some combinatorial or polyhedral structure that one can associate to the boundary of a compactification, that which is in the context of this pair of varieties at infinity. Okay, the setting I would like to focus on is a particular, very classical setting of the tropicalization, the tropicalization of the moduli space of abelian varieties. The moduli space, the classical moduli space of abelian varieties, AG, denotes the moduli space. So parameter space for isomorphism classes of abelian varieties of dimension G. For experts, I will totally omit the issue of polarization. So just as a parameter space, the points correspond to isomorphism classes of abelian varieties of dimension G. There's a lot to say about this. It's not a priori at all clear. It's very interesting that this space has the structure of a complex variety. And what I'd like to do is to tell you, unfortunately, without too much sort of time for motivation, but let me tell you what happens for AG, sort of in analogy to the simple example that we started with. So, roughly speaking, here on this slide, I gave you an example of a compactification of a torus. And actually, or perhaps some of you are familiar with the machinery of toric varieties, toric geometry in general, that gives you a way to, put into a machine the data of a polyhedral fan, a rational polyhedral fan in an appropriate sense, and get out if you put in a complete fan, you get out a compactification of a torus. There's an analogous story here for varieties of a particular form called locally symmetric varieties, provided by old work from the 70s of Ash, Mumford, Rappaport, Tai, that give, it's complicated, but you can think of it to start with as a sort of analog to the toric geometry machine that takes a fan as input and spits out a toric compactification of a compactification of a torus. So this is the machine called toroidal compactifications of a class of varieties called locally symmetric varieties. Sorry, locally symmetric varieties. And AG is one such example. And I want to tell you, unfortunately, without too much context, but let me just dive in and tell you what machinery, what the combinatorial inputs are to their machine in the particular case of AG. So now it's time for me to define the tropical moduli space of abelian varieties. So let's start with, so fix a number G. And we'll start with something that we all agree, I think, is important and central. It's the cone of positive definite matrices, symmetric G by G. Symmetric, positive, definite matrices. So these form, so they're a subset of a G plus 1 choose 2 dimensional real vector space. And this subset is an open cone. It's an open convex cone, by which I mean it's convex, and it's closed under scaling by positive real numbers. This is a picture, it's actually sort of a true picture for G equals 2. If you consider G equals 2, the space of symmetric matrices of size 2 by 2 forms a 3-dimensional real vector space. And inside, we have an open cone of positive definite such matrices. As usual in tropical or toric geometry, it's sometimes annoying to keep drawing pictures of cones. So we may just take a slice and draw the link, the so-called link of the cone. So the equivalence classes under the relationship of scaling by a positive real. So I might then draw PD2 just like this. Okay, there's an interesting partial compactification of the link that will be important to us. This is the so-called rational closure. So the rational closure it's slightly bigger than the positive definite cone. It consists of those PSD, so positive semi-definite matrices, with rational kernel. Let me explain. So positive definite matrix, positive definite symmetric matrix is one with all positive eigenvalues. Positive semi-definite matrix is a slight relaxation. You're allowed to have eigenvalues that are 0. But we ask that the kernel of your matrix, whatever it is defined over Q. In other words, generated by vectors in Q to the G. So the rational closure, maybe I can draw it up here. You know, in the link, we're adding a dense but countable subset of points at the boundary. Why we're doing that, I will need to have another conversation. I'm happy to talk about that afterwards, but let's take it as interesting for now.
So this is not actually closed in the real topology?
That's correct. It's not closed in the real topology. But what it is the following. So we're sort of getting ready to study an interesting action of an arithmetic group, the group of lattice automorphisms, in other words, invertible integer matrices G by G on PD, which extends to an action on PDG rat. After all, a positive definite matrix can be conjugated by an invertible matrix. So the action is, you know, AX goes to AX A transpose. And this amounts to an integer change of basis regarding your positive definite matrix as providing the data of a bilinear form. So what we're going to be interested in is let me just write, so the space PDG modulo this action is interesting. It is a moduli space of real tori with flat metric, so flat real tori of dimension G. And it is an example of a so-called locally symmetric space in the sense of differential geometry. So, here's another picture. I'm going to draw the same picture again and again. This is a picture of, it's actually a sort of accurate picture of PD2, the link of PD2. And there's an arithmetic group acting on it, GLGZ. And it's not obvious at all, but there's a fundamental domain looks like this. And what we're interested in doing is sort of compactifying that fundamental domain. So in order to do that, sorry, this is too fat at the end. In order to do that, we'd like to add 1 point to the, like in this picture, in the case G equals 2, we'd like to add 1 point in the link. But we're doing it in the other order, whereby I would like to, in what is on the screen, we started with like an open convex cone. We took the quotient by some group, and then we compactified. Instead, I'd like to do it in the other order. I'd like to sort of partially compactify the open cone such that it is ready to become compact upon passing to the quotient. So that's what I'm doing here. I've added essentially all of the orbits of the points that I'd like in my compactification. Let me actually now get to the definition. So definition. This is remarkable combinatorics associated to, it's called the second Voronoi decomposition. And this is what I will describe is a polyhedral tiling of PDG rat, of the space of positive semi-definite matrices with rational null space. That polyhedral tiling is necessarily infinite because the whole thing is not polyhedral. But the cones are permuted by the action of our group into finitely many orbits. And the combinatorics is remarkable and goes back to Voronoi in 1908. So the combinatorics is as follows. So suppose you have a positive definite form with rational null space. Then it has a so-called Delaunay subdivision. This is going to be a infinite polyhedral periodic tiling of R to the G, defined as follows. So, okay, let me describe it sort of in story form. So what you would do to compute the subdivision is you consider inside R to the G cross R the points of the form x comma x transpose qx, where x ranges over all lattice points. I'll give an example. So here, this x, like my notation is not optimal. This x really means like g coordinates. So you take your g into like coordinates of your lattice point, then you plug in that lattice point into q. Here q is viewed as a quadratic form. So I'm writing x transpose qx to communicate the output of q viewed as a quadratic form on x. So what we have here is a list of points in R to the G plus 1. And if you view them, if you take the convex hull then there will be some polyhedral structure visible from minus infinity. So let me just write it and then we'll do an example. It's the polyhedral tiling, infinite periodic polyhedral tiling of R to the G obtained as the projections to R to the G of the faces of this convex hull. And now let's do an example. Let me do two examples, in fact. The first just to get our bearings, and then the second in G equals 2. So the first is G equals 1, just so you can maybe see what I'm talking about. So consider the 1 by 1 matrix 1, which as a quadratic form sends x to x squared. So the output, the Delaunay subdivision of Q, is the following. So to compute it, you lift not all points of R, but just the lattice points to the prescribed heights, the heights prescribed by the form Q. So 0 is lifted to height 0, 1 and minus 1 are lifted to height 1, and so on. If I lifted everything, I just get a picture of a parabola. But now I have a sort of discretized parabola whose convex hull has faces which are visible from below, from sort of height minus infinity, and projected give you, in this case, admittedly not so interesting, infinite periodic tiling of R. Let me do one more example. G equals 2. So let's do the quadratic form x squared plus xy plus y squared. So the corresponding matrix, I believe, would be 1, 1 half, 1 half, 1, communicating that quadratic form. So to get the Delaunay subdivision, you do the same thing as before. You take all the lattice points in R2, and you lift them to height prescribed by the quadratic form. For example, well, it's hard to draw, but I'll just write the heights as numbers so you can try to picture it. For example, I lift the point 1, 1 to height 3, since Q of 1, 1 equals 3, and so on. So let's see. I think I get the following. And then it takes some thinking, but you have to imagine this sort of discrete paraboloid above, and it's and what it looks like from below. What you get, again, is an infinite periodic tiling of, in this case, R2. In this case, it looks like this. This is a picture of the Delaunay subdivision associated to Q. So associated to every point in my rational closure of the positive definite cone, I have a picture, a particular polyhedral tiling. Now, given one of these pictures, so given any such picture, a Delaunay subdivision, let's collect together all of those Q's that gave rise to it. So collect together all those Q's that gave rise to, so such that the Delaunay subdivision of Q is that fixed D. Then we claim, we'll say this is a theorem, the closures of these sigmas as D ranges over all Delaunay subdivisions form an infinite face-to-face polyhedral decomposition of PD G rat. And furthermore, GLGZ, this arithmetic group, acts by permuting cones, so that the tiling is compatible. Sorry, this polyhedral decomposition is compatible with the action of GLGZ. Sorry, permuting cones, and crucially for applications into finitely many orbits. Let me try to draw one last picture that sort of puts this all together. So here is a picture again of the link, really, of PD2 rat. And the Voronoi, the second Voronoi decomposition, in this case, it's the only one that's really possible to draw, so I'm doing it. Looks like this. So it is indeed an infinite face-to-face tiling. The maximal cones here all form one orbit under the action of the group. And each cone, remember, collects together those matrices, those positive semi-definite forms that give rise to one fixed picture. So for example, this upper triangular cone gave rise to that one. This is exactly the one we studied. Somewhere in here, there's the matrix we studied. And as you move around, you get other such tilings. And I can leave it as an exercise to fill in the rest. So this is the second Voronoi decomposition. And the definition of the moduli space of tropical abelian varieties. Of dimension G is the quotient of this tiling by the action of GLGZ. There's a bit of a subtlety here. You might just say, what did the tiling have to do with it? And the answer is that it imposes a sort of different topology. So when I write PDG rat Voronoi, I mean the topological space that you take by just taking, that you get by taking each of these cones, all of them, and gluing them combinatorially according to the diagram. It's a little bit different topologically. For example, this point here has an open neighborhood that looks like this red region, which is not true in the induced topology. This is the moduli space of tropical abelian varieties, and it actually furnishes a moduli space of certain objects that deserve to be called abelian varieties in tropical geometry. But I don't have time for that portion of the story. Let me conclude by telling you some interesting facts that maybe will at least whet your appetite. So this AG trop was not sort of synthetic. It really is the tropicalization of the of a certain toroidal compactification of the variety AG. So it's the combinatorics that arises and indeed provides the input for a machine developed by AMRT in the 1970s that you can think of, to very rough approximation, as sort of analogous to the machine that spits out a toric variety from the data of a fan. And maybe I'll just end with maybe a intriguing, perhaps, theorem statement, joint with Brown, Galatius, and Payne. It says that the compactly supported cohomology of the space AG trop, these spaces are interesting. It may not be visible from the G equals 2 example, but if you consider all of them together, and consider the cohomology with compact supports over all degrees, then what I've written here is a bigraded vector space, and one of our theorems in our long paper says that this bigraded vector space admits the structure of a Hopf algebra. This is somewhat surprising, and there's more to be said, but maybe I can just end with this theorem and mention that the proof involves connections to actually the algebraic K-theory of the integers and to a theory of K-theory of graphs that we construct in the paper. Okay, thank you for your time.
Questions for Melody?
Hi, Melody. Thanks for the really great talk.
Hey, Sam.
This question is really like naive and just based on your picture of the circle divided into these triangles. But to me, this looks like sort of something like hyperbolic geometry. Is there any connection to that here?
Yes, actually, this particular picture should look like sort of the picture of the hyperbolic plane. Yeah, this is a picture of like a locally symmetric space. So there is a Riemannian structure. Well, okay, yeah, so there's a Riemannian structure, absolutely. And like this may or may not look also like the usual picture of how to compactify the moduli space M11, perhaps, of elliptic curves. I don't know if it sort of looks similar for that reason.
Okay,
Um,
thanks.
yeah, thanks.
Okay, Art has a question also.
Yeah, mine might even be more naive. If you could go back, I think it's one slide when you built the diagram for G equals 2.
Yeah, I may have made a typo, so
That's fine. So I think 3 and a 1 should swap. So I think I understand why the diagonal lines are there. Those are connecting things that have the same value. Excuse me. What about the horizontal and vertical lines? Why are those there? Or am I
okay, let's see.
misunderstanding something?
So what this is meant to be a picture of is like imagine each of those lattice points Z2 popping out at you at height written. So the origin is at height 0, certain points are at height 1, etc.
Yeah.
So then you have to imagine taking the convex hull of this this discrete set of points. These are points now in R3.
Okay.
And like, one dimension down, it looked like this, but it's a little harder to draw. So the best I can do. So once you take the convex hull, you have a sort of like triangulated paraboloid surface visible from below.
Okay.
This is the projection. Yeah. So, I mean, I guess the precise statement would be that, for example, I drew this triangle because there exists an affine linear functional that takes values 0 at the origin, 1 here and 1 there, and takes values strictly lower than all of the other prescribed heights.
Okay. Great. Thank you. That's very helpful.
Thanks, Art.
Okay, I think we have time for one last question from Dale Worley.
Okay, in regard to that picture you've got right there, the integer lattice points, do they always show up as corners of the simplices in that decomposition?
Yeah, in this case, yes, but there could be more degenerate pictures. For example, if you take an actual Q on the boundary, then you get polyhedral regions that are actually not finite. So you would get, for example, slicing R2 into infinite strips.
Okay, so that taking the convex hull can wind up eliminating some of the integer lattice points.
That's true. Yes, they won't all be visible as vertices. That's true.
Okay, cool.